We've been waiting for attendees to hit the 100 mark, and then we then we kickstart. So let us follow the same principle today. So welcome everyone again. The final day of the conference is packed with many sessions, including main conference, doctoral consortium, and last but not least, the closing, where we will have a glimpse of next year's conference. So let us kick off the day with our third and final keynote. It is my great pleasure, of course, to introduce Professor Felix Naumann. Felix, I've known for many years. He's a man of many talents. Started with studying mathematics, economics, and computer sciences at the University of Technology in Berlin, and then went on to do his PhD in the area of data quality at Humboldt University of Berlin. Felix has a stellar record of diverse experiences, including work at the IBM Almaden Research Center, the QCRI, AT&T Research, and SAP. Since 2006, Felix is Chair of Information Systems at the Hasso-Plattner Institute, HPI, at University of Potsdam in Germany. His research has spanned many exciting topics, including data profiling, data cleansing, data integration, with over 200 scientific publications. Felix is also the trustee of the prestigious VLDB endowment and will be the PC co-chair for VLDB 2021. Imagined to be one of the first conferences brave enough to do a full hybrid. Big job and good luck. So before we start, the usual reminder for everyone that questions are preferred through the Q&A function of Zoom. But you can also raise your hand if you wish to ask through audio. We can unmute you. And at the end of the presentation, we will try to get through as many questions as possible. And if there are any remaining, we have been following this process of then communicating those questions to our keynote speakers, who have been kind enough to do their responses retrospectively, and we will make those available. So with that, colleagues, please join me in welcoming Professor Felix Naumann as our keynote speaker. Felix, over to you.
Thank you very much, Shazia, and thank you very much to all the organizers for inviting me. Of course, it's my great pleasure to be here and give a keynote and give a little bit of insight into our work, right? And the topic I chose, as discussed with Shazia, was about data cleaning, data quality. And I have some background in this work. And more recently, I've turned into this area of data preparation that I wanted to talk about. And as you just saw, when I give the title Bad Files, Bad Data, Bad Results, basically I'm speaking about what Michael on Tuesday talked about, actually on Wednesday, about low trust. When we talk about bad data and bad results, this in effect, of course, causes low trust in data. Okay, so I'll give my spiel about big data. Yesterday, we already heard Sudha give her explanations and the background on big data and the 4 Vs. So I'll give you a little bit of a different insight just to emphasize how important good data quality is, right? So Jim Gray, the late great Jim Gray, basically set up this image of that we're in the 4th paradigm of science. So the first was empirical experimental, trying to find out what nature is about. Then came a theoretical understanding of the world by trying to build models or understand nature by explaining it with models. Then came the computational revolution with computers, where we started to do simulations so we could simulate nature. And now we're in this data intensive phase where data and data tools try to support the whole research cycle. So this is an important part. Again, I won't give you this the spiel about big data. Sudha already made it very abundantly clear yesterday. You know, if you stack DVDs from the Earth to the moon, that's not even close to the amount of data that we have at the moment and that we will be producing. And of course, we want to put this data to good use. There's a great article. It's already, as you can see, many years ago, but it was really, really interesting. And I think it's still true today. The end of theory through big data and data science. So there's this nice quote by George Box saying, the statistician saying that all models are wrong, but some are useful. And then Peter Norvig of Google extended it, saying all models are wrong and we can succeed without them, right? So before big data, we always said as scientists, correlation is not causation, but somehow we're starting to say, actually, correlation is enough. You know, I'll sell my products based on correlation alone, right? And you know, a little bit scary. And so we want to at least get the data part right. In essence, what we're doing as data scientists, we're comparing nice models like the gravitational law with Newton by data. So if I observe apples to drop often enough, I'll believe that they'll drop in the future without understanding why this happens or what law or model is behind it, right? But then, of course, you know, you might have a little bit of oranges in your data. So, so it is important to get the models right and then to be able to rely on them, okay? So this is a typical data science pipeline. And I do want to point out that a significant portion of the pipeline, from my point of view or from my definition of what data science and data engineering are, is an engineering side, right? So the traditional data science is on the right, and data engineers are responsible for getting the data ready to be analyzed and used to train models, let's say, in a typical data science setting. Right? And today we'll be focusing mostly on that left corner here, extracting data from files and curating data, cleaning data. That's the topic of the talk today. And of course, every single box that you see on the screen is a significant, huge research area. And so also for this box here, or these boxes here, I'll just give you some insights. The goal of my talk today is to, let's say, let you appreciate the problems we're trying to solve and get first ideas of how to solve them. Okay. So data preparation is a complicated field in data curation. So there's this very nice, also a few years old survey about what data scientists do all day, right? So we train them at universities on all the nice deep learning models, artificial intelligence systems, et cetera, but then they end up using 60% of their time cleaning and organizing data, and another 19% of the time collecting the data from the web, from other departments, or getting it out of systems, right? So that is super annoying. This survey has been repeated a few times, and the numbers always stay the same. So we educate people, and they're great. They have great minds for this area here, but they end up spending most of their time doing menial work like cleaning and organizing data, right? And then this survey continued asking, what is the least enjoyable part of your job, in essence, right? And the numbers are almost the same. So it's exactly cleaning and organizing data and collecting data sets. So it's the least enjoyable. It takes the most amount of time. And it doesn't really need, you know, huge expertise, right? So I think there's a huge research potential here. Not only so of course there's already a large research area in data cleaning and data preparation. There are tools out there, and I'll give you a few highlights, but I'll also show you why even tools are not up to the task quite yet. Okay. So this is the structure for today. We'll look at some examples of bad files. Of course, I don't mean that they're bad in their you know, in their spirit, but badly formatted, let's say. And then look at some data preparation ideas to, you know, get a handle on them. And then look at bad data and some data cleaning techniques. And of course, we'll have an outlook in the end. Okay. So this is a typical example. You download a file from the web, and you look at it, it looks, you know, a little bit messy, but, you know, it looks kind of reasonable, looks like a comma delimited file. You already might notice some slight problems. You can see that all terms are quoted twice. You know, this happens when you import and export and re-import and re-export data. You know, strings get, you know, get quoted again. This is kind of okay. We should be able to deal with it. But there's one worse problem that is much more difficult to spot. That in fact every line begins with a quotation mark, and let's see where I can find one, and ends with a quotation mark, right? So the entire line is quoted as a string. So when you start loading this data, a typical system will just think there's just one column with a very long string in it, right? And this is just annoying stuff, right? Of course we can clean it, right? And you know, average computer scientists would need maybe 5 minutes to get rid of these quotation marks, but you have to discover this problem first, and then you have to spend those 5 minutes. And that's exactly one little block in that 60% data preparation that we'd like to alleviate. And of course, it will be good if this is the only problem and that's always the same problem, but of course, problems are very different. This is an open data file. And again, it looks kind of reasonably formatted and kind of nice. But what you'll notice is that right in the middle of the data, you get some totals, right? Some aggregations. So how annoying is that? So if you want to import that data, you need to get rid of all these lines to do this properly. And this set of, I don't know, 6, 7 lines repeats again and again and again throughout the file without any great distinction. So again, you'd have to write a filter that kind of looks at these values and says, okay, filter out all rows that have the keyword total in the country of nationality, right? Again, it may take just 10 minutes to do this, but you have to realize that this is a problem first, and then you have to spend those 10 minutes. Right? And of course, we're not the first to understand that open data and you know, open data, government data has problems. So Shazia also published together with Marta a very nice article precisely pointing out this kind of problem that, you know, it's not enough just to dump a lot of data out there. It has to be of good quality and it has to be useful. Right? One more fun problem that I found, I mean, this is great, right? So you have a nice file with lots of data, and then suddenly a few data values here in the middle are left out, and instead replaced with the string, data are confidential, right? So try reading those files, right? Super annoying, doesn't work properly. And of course, it's even worse if those kind of lines appear, let's say, towards the bottom of the file. You have a long load process. You've waited for 1 hour for the data to load, and then suddenly it breaks because of this kind of stuff, right? Why is this a problem? Because we have many data sources that gather data from all sorts of places, and they're created in many different ways, right? So you've probably heard of this concept of data lakes collecting a bunch of data, maybe for a specific purpose, but from many different sources. And one of the main selling points of data lakes is the idea to just dump the data in there and then see later how you want to use it. But that precisely is part of the problem because everything is just dumped in there, right? Open data is also, comes from many different sources. You have many different machines that produce different formats of data and have kind of different error levels of their own. Right on the right, you see the opening page of data.gov, and you already see a little bit something scary, right? So this very first data set already is provided in 4 different formats, right? Okay, you could say that's convenient until you realize that you can filter by format, right? And then you have this filter, you could export data as HTML, XML, PDF, TIFF, XYZ, whatever that is, right? But then if you want to show more formats, you get all of this. So this is all the kind of formats that you can get out of opendata.gov. And you can see it's all sorts of stuff, right? And so we did one quick experiment trying to extract all data about tornadoes from data.gov, and we got 20 different formats just for this one very tight domain, right? Okay, so these are the kind of problems that we want to fix, and that's what I call data preparation. The term data preparation sometimes covers a larger area of research. I'll get into that when we transition from data preparation to data cleaning, and I'll try to point out the differences here. For me right now, data preparation, I'll focus on cleaning up files and being able to simply load data into a system to then later on clean errors in the data. Okay, so here you can see this is the kind of problem that we want to address, right? Wrong formattings, encodings, these kind of things, right? What we did just to get started is try to find out, okay, what kind of problems are there? So these are all tools that support data preparation, and they've defined what data preparation is. And much of this is really formatting things, right? So being able to check for ranges, formatting date columns, enrich data, split columns by the space characters. So for instance, split first name, last name, change column types from integer to string, all this kind of stuff just to massage the data, right? What we realized though then, once we looked at all this, is these are all very nice tools. They have cool functionalities. Some are even a little bit intelligent. They suggest what you should be doing to your data. But a prime prerequisite for all of those tools is that you've loaded the data into that system, right? And that's where the real problem starts, because getting data into that system is actually not easy at all. So I wanted to highlight a few of our projects, basically all with the same goal: the ability to load data, to ingest data into any kind of system. And while I'm introducing just very briefly these projects, I'll show you what kinds of problems we encounter and just very quick ideas of how we approach them. Okay. So the first problem that we want to address with our Mondrian system is to dissect multi-table files. So often you have files that contain multiple tables, right? So if you look at this file here, again, all examples I'm showing are real-world examples. I've made nothing up here. These are all, actual data files that are useful for a specific use case. So you can already see this is kind of a mess, right? And we annotated this, and this is basically, these are the sets of, let's say, coherent pieces of data. Not all of it is data, obviously, but there is some tables in here, and we'd like to be able to recognize this. And here you can already see why we called the project Mondrian, because it does remind you a little bit, at least, of Mondrian paintings here. Right? So we want to understand this is a multi-table file, and then ideally we want to extract the data. How do we do it? We use a visual approach by transforming data into pixels. Basically, if there's data, it will be a pixel. And then we use image recognition techniques to understand and cluster different parts of the image and saying these are parts that belong together, and thus understand, okay, this is one part of a file, this is another part of a file, this is a table, this is a table. Right? And we go a step further and understand that many files follow the same layout template, right? So if you've understood the template of this file here and know how to extract the data and realize these files follow the same template, because we can automatically recognize that, we can apply the same kind of extraction from that file, even if the files have a slightly different organization. If they're from the same template, we can reuse any kind of code that we have to extract data from one file. Okay, so this is a first idea. We have multi-table files, and now we're able to identify individual parts of those tables. Okay, so now we have those individual tables. Now we need to extract them, let's say, into a common CSV format, even though they might be formatted differently. So we have a project called Extractable. I love that name. I didn't come up with it. I'm showing you two different kinds of formattings in data. So on the top left, you can see this is, kind of ugly, but it makes sense. The problem is with this kind of things, this is a visual layout. Right? So there are a different number of spaces between these values. And if you want to extract the data, you need to understand that, you have to parse a few spaces until you get to the next column. And this might be different from row to row. Right? So that's already one problem. Another problem is files like this, a very nice table, human readable, right? But you have to understand what part of the table is actually data, so that you have to get rid of all these lines. And we want to do this automatically. Right? And just to point out, just as a fun fact, both of these screenshots are from the very same file, right? So you can see what kind of mess we're dealing with here, right? So how do we do this? How do we figure out that this is the data and extract it to CSV? Again, we have kind of an approach where we encode values in null values or missing values or white space versus actual values. And then we recognize, for instance, that this is a long block of white space. This is a shorter block of white space. So our assumption right now is this is the separator. Then we go row by row. And in the end, we find basically these patterns of white space that reach a significant part of the file, and then that's how we separate out the values, right? And right here it looks quite simple, but in reality, of course, it's different because you also have white spaces in the middle of values, for instance, and a human can easily understand this, but for a machine, it's actually not quite so easy. Next step, once you've done this, we want to identify ill-formed records. This is precisely the problem I I mentioned earlier that you have a file that looks kind of nice, but there might be a few lines that are problematic. So this is a reasonable file, but of course, if you'll realize immediately that there's a problem here and a problem here, and your load process will probably break at that point, or it will ignore those lines, leading to missing data, etc. Right? So we want to automatically recognize these kind of lines. Right? And so how do we do it? We use a pattern-based approach. So we try to extract patterns from individual cells, from entire columns, and then put together column patterns to typical, frequent, and significant line patterns, right? So we want to look for patterns that are true for many lines, right? And so you can see two example patterns at the bottom where we basically encode. This is a sequence of digits. This is a numeric column. These are some uppercase letters. And we look for patterns that appear frequently enough. And then we say, okay, well, those patterns that appear frequently are probably the data, and infrequent patterns like this one here is probably an outlier line that we shouldn't read, or we should alert the user to this line and say, before you load your data, have a look here because it might not work. Okay. So in a sense, next problem solved, right? And then, as I mentioned earlier, there are many files that are formatted very nicely, but they contain, let's say, aggregate cells or other kinds of cells in the middle that we want to recognize. So we have a cell classifier. If you get a table like this, we'd like to be able to understand that this top stuff is not data, it's just metadata. There's a footnote here, right? There are some group headers here that repeat once in a while. Right? You have aggregation rows, header rows, data rows, etc. Right? And we've annotated hundreds and hundreds of files also for our testing. And this is kind of then how it looks. Every shape looks a little bit different. So if you want to use this data and not rely on a human actually marking the columns and rows to extract, you need to be able to understand what kind of cells you're looking at. Right? And so our approach is a machine learning based approach. We look at the cell itself. What kind of value does this cell have? Then we look at the surrounding cells. So we have a context. We look at the column to the left, the column to the right, the row above and the row below, and see what kind of data do I see here. So for instance, if I see an empty line above, then it's not unlikely that this is a header row actually and not a data row, just to give you one example, right? And then we also look at the values above and below and to the left and to the right to understand, is this an aggregation or not? So we try to sum up all these values and see if the sum is in fact that value, right? So we do all these kinds of patterns and get quite good results in classifying individual cells. And then if you're interested only, let's say, in the data cells, you can extract only those and get rid of all the junk around it, okay? But then we realized this aggregation, that's kind of the weak spot, because aggregations are actually very difficult to spot. Here, it seemed easy. You just sum up everything above and then find out, ooh, lo and behold, this number here is in fact the sum of everything above. But life isn't always that easy. You have nested aggregations, you have different, you just don't always have sum. Of course, you have differences and averages, et cetera, et cetera. So there's one more project that we're looking at is to find aggregations. So here's kind of an extreme example where you have all sorts of kinds of aggregations all over the place, right? So for instance, this value is a sum of these three values here, right? So you can't even just take all the numbers above a value. You have to kind of choose every second one and understand that these are percentages that are referring to something else, right? So we want to be able to recognize these kind of aggregations automatically. And again, we're assuming here that we have, the raw data files. So we're assuming that we have CSV files, and that is the most common form in which these kind of files are exported. Of course, I'm sure some of you are thinking, well, what if I have the Excel file? I could see the formula. First of all, in many Excel files, you don't have the formula anymore, but often this stuff is exported as CSV, put on the web, and it's up to you to figure out what's going on, okay? And one interesting observation that we made when we annotated, again, hundreds and hundreds of files, is that aggregations are actually not always true, right? There's often a difference between the true number and the observed number because of rounding problems. right? And actually the highest observed error level in files that we found is 37%, right? So quite a high error. And in fact, almost 30% of all aggregations have an error, right? They're not always exact. So it's not enough to simply, let's say, sum up a bunch of values and check if that value is the same as a number below it. You have to account for some kind of error. And of course, we do that, and again, are able to recognize aggregations pretty reliably in CSV files. Right? This is our system. We have basically detectors for every kind of aggregation. So we have a sum detector, average detector, etc., etc. Then we have a second phase where we do a collective aggregation detection. The thinking here is the following: if I have a column and a sum, and then I have another column and another sum, it's more likely that this entire row is filled with sums of the columns above them, right? Rather than something mixed, that a sum is maybe a little bit higher or a little bit lower. We do assume, or we hope for, let's say, kind of a structurally well-behaved file in most cases, right? And then finally, we have a final phase looking for nested aggregations. So sums of sums or averages of sums, these kind of things also happen in files. And so in the end, we come up with some good results. I'm not presenting any of the results that we're showing. I just want to give you some ideas of what we do. I can tell you that on average, precision recall in all of these things are around about 80–85% or so, right? So, you know, there's no magic, nothing always works automatically. So these tools and ideas that I'm presenting are there to help users along. Okay. And then finally, we kind of got fed up with state of the art and said, okay, let's devise a benchmark for data ingestion. And we're doing that at the moment. And how are we doing it? We're feeding lots of interesting data sets to tools like Pandas or LibreOffice or MySQL or Tableau, and see how well can they deal with problematic input files, right? And as you can see, a very typical error here at the bottom, you know, an error tokenizing the data. They expected, or Pandas expected 25 fields, but saw 27 fields, and then just aborted, right? That's annoying, and we want to measure how well Pandas and all these other systems handle slight problems in the files. How do we do that? We inject those slight problems into the files and then load and then export again and see what changed, right? What was removed? Did it even work? Was there new data that was invented by these tools? It does happen that they just add a column and think they're doing something intelligent. So we have these kind of problems. And on the right, you can see our, again, results of our annotation. So you can see the kinds of problems that we are injecting into files are real problems. So they do happen in truth. So file encodings, for instance, are often difficult for systems to understand. Right, and so we are creating this benchmark. Each benchmark run has about, let's say, 50 files or so, and then we import, export, and see how well the tool did. Okay, so let's move now slowly from data preparation to data cleaning. So I've shown you all these kind of structural problems. So my definition of data preparation is that it adds syntactic and structural value to problematic data and problematic files. So it's more at the structure and syntactic level, while data cleaning is more about semantics. It corrects errors in the data that are not values that are ill-formed. These are values that are just wrong, right? For whatever, let's say, business reason, right? And of course, the spectrum between data preparation and data cleaning is not well defined. If you just think about normalizing date formats, right? So, you know, getting the format right is one part, but understanding that February 30 is not a valid date already has some semantic flavor to it, right? So it's not, you know, for many of these things, it's not quite clear, is this data preparation, is this data cleaning? There are some folks that just say data preparation is the overall term, and it includes everything I just talked about, plus data cleaning, plus feature engineering for AI systems, and they call all of that data preparation. I think it's useful to make a little bit more fine-grained distinction. Okay. Okay, time for a little breather. So this was about files, and now basically my assumption is we've ingested the file, and now we want to find errors, right? We want to do data cleaning. What could go wrong here? Right? And I'll give you some nice examples here. Where do these errors come from? Well, real world data is raw and dirty. So what you see in the background here is a famous example by Google. These are all searches, let's say, by teenagers looking for their favorite singer, Britney Spears, but have no idea how to spell her. So these are all the different spellings, and Google prides itself to map all of these spellings to the singer Britney Spears, right? But that's how errors happen. Another fun example, you might have heard of this, but I just love it, is this notorious driver in Ireland called Prof, who gets parking tickets, speeding tickets all over the island, right? And he's supposedly from Poland, and then it turns out though that Prawo jazdy is actually the Polish term for driver's license, and it just looks like a name, and policemen have been entering that name and giving that person tickets based on that supposed name. Right? So these are kind of nice sources of error. Why is it important? Well, there are many, many studies that show that poor data quality has significant impact on your business. Often these numbers are kind of pulled out of thin air, I believe, but there's also some hard data to show what the problem was. Every year you read about these kind of news articles. You can see one on the right that the IRS is unable to mail you the check. And do keep in mind what's going on here. People write their tax form, fill out their tax forms, send it to the IRS, expecting a check in the mail, but don't get their address right. And so the check cannot be delivered, right? So you think people are especially careful here, but these kind of errors still happen. Right. Here's another example. This return rate of 7% is a number you read again and again. If you send out 100 mass mails, not emails, postal mails, you'll get about 7% back, right? And if you're a company sending out, let's say, 1 million bills every year, you get 7% back. So this translates to huge stacks of mail that you have to correct manually. Obviously, this is a problem. Okay, you can see some other effects here as well. Here's a kind of a fun thing that we did with a partner in Germany, a cooperation partner. They had a table with all these fields here, right? Name 1, name 2, name 3, city, district, street, etc. And in this cross matrix, they filled out what kind of data they found in those fields, right? So for instance, in 2,600 cases, they found the mobile phone number in the district. Why? Because there was no other place to put the mobile phone number. So people said, well, district is not important. I have the city, so I'll just put the mobile phone number there, right? Or an embargo or deletion flag, right? To say, don't deliver to this customer, right? There's no good place to put it, so they put it into name 1 or name 2, right? And they said, do not deliver, right? Instead of the actual name of the person, right? So again, all of these are errors, right? Everything you see here as a sum at the bottom, every single item here is an error in the data. Okay. So data quality is a broad research area. As a computer scientist, I like to focus on things like accuracy, completeness, maybe amount of data. But data quality has a much broader range, and you can see some of the things that Michael Roseman talked about yesterday, like believability, understandability. These are also very, very important aspects. They're just much harder to assess, to measure, right? And you can see this broad range. There was a nice study by Wang and Strong who collected these 179 dimensions and then boiled them down to the 15 that you see in the middle. And this is kind of a common community understanding of the important dimensions of data quality, right? So this is a very broad field. Again, in this talk, I'm focusing on the, let's say, more hard, not difficult, but more the hard core problems of getting the data right, as opposed to making it believable or securing it, etc. Okay. Okay, so let's look in the last few minutes a little bit into data cleaning. So how do we actually correct these values? There's a great survey by Elias and Chu that I really recommend. And they basically said, well, we have two problems. We need to detect errors and we need to repair errors, right? And they have this classification. First, what kind of errors could there be? And they basically said we have integrity constraints, so business rules, let's say, and we have data deduplication as one other big family of problems that we'd like to clean. And then, of course, how do we detect errors? Well, we can try to find automatic methods to detect errors, or we can do this in a human-guided way, you know, with experts, basically, right? And then the repairing techniques have the same kind of a classification. How do I repair? You can try to find, you know, repair errors one at a time, saying, okay, what about this value? What about that value? You might have rules to repair the data. And again, you can do this in a human-guided way or an automatic way. Okay. Very briefly, what kind of things do we want to detect to find errors, right? A typical thing, as I said, are integrity constraints, so business rules. So a very typical thing is a functional dependency saying if two items have the same zip code, they should also have the same city, right? This can be modeled. And if we know that this is a rule, we can easily detect these kind of errors. Right? But there's also more expressive things, so-called denial constraints that are quite expressive. So this particular denial constraint says, if you're living in the same state and your income is higher, you cannot have a lower tax rate, right? That's a reasonable rule. And we'd like to check our data for those kind of problems, right? And if you think it's difficult to come up with these kind of rules, well, you can ask experts to write them for you or explain business rules for you and you write them. But there's also some automatic discovery methods in this area of data profiling that run through the data, extract rules that are true or almost true for the data at hand, and then show those rules to the user and say, or to the expert and say, look, this is a rule that is almost true in the data. It looks reasonable. Do you think it should always be true? And then the user might say, yes, actually, that's a very good rule. Please check the rest of my data for this. Okay. And then the next step, what to repair. I'll give you the same example and give you a really nice idea that I've stolen. I'm just citing basically the HoloClean paper. It's a paper by some great colleagues who've tried to find so-called minimal repairs. So we still have the same integrity constraint, zip code determines city. And if you look at the data at the bottom, you'll find a problem. You'll find out, okay, this zip code and this zip code is the same, but the state in this case is different, right? That cannot happen. And so any of those four values could be repaired. Maybe New York is wrong, should be Arizona. Maybe Arizona is wrong, it should be New York. But maybe one of the zip codes is wrong, and it should be a different zip code, and somebody just inserted a typo. We don't know, right? The second second constraint up here is a denial constraint, in this case saying a manager in the same state should always earn more than an employee in that state. I don't know if it's a nice rule, but let's say that's our rule. So we have two people in the same state, New York, New York. One of them is an employee, one of them is a manager, and lo and behold, the manager earns less than the employee, thus violating this rule. Right? And now, if you look closely, you'll identify that a minimal repair would be to repair this state here. If I repair that state, let's say set it to Arizona, all the problems are gone at once, right? So we try to find, the colleagues try to find those minimal repairs that repair as many violations of rules as possible, right? I think this is a very neat idea. Of course, it's not necessarily correct, but it's a reasonable approach to minimize the fiddling around with the data to just get everything right. Okay, what else to repair? Why is this not forwarding? What else to repair are so-called duplicates. This is a fun area. I'll just give you a very brief insight into this. So you can see on the right, this is a letter I get twice a year from a financial company. They're trying to get my money, and I say, well, if you can't even get my address right, then I'm not going to give you all my money, right? Obviously, right? Why is it difficult to detect that this is in fact the same person. So first of all, let me point out, the mailman gets it right. I get both letters, right? But in the system, I would like to be able to clean this. The problem is the representations are not identical, as you can clearly see. And the other problem is that the data sets can be very large. And in principle, you have to compare every record with every other record to get this right? And if you have, let's say, only 10,000 customers, you're already looking at 500 million comparisons that you need to be making, right? And that's clearly not feasible. And every comparison is expensive because you're applying some kind of a similarity measure. Okay, so where do the problems come from? This is from CAiSE's Hoover website. So Will, if you're listening, I think this is fixed by now, right? But you were registered 3 times somehow. And so suddenly if you do counts of the number of attendees, you know, these are wrong aggregates. You'll get 3 emails for every notification, et cetera, et cetera. So these are the kind of problems we want to fix, right? And this particular one I saw this morning is fixed already. Okay. Ironically, duplicate detection has many duplicates, so it needs to be duplicated in itself. It's commonly also known as entity resolution or object identification or record linkage. These are some of the popular terms for the very same kind of problem. Okay, so how do we do it? As I said, we need to make all comparisons. We need to compare every record with every other record. Very, very expensive and very difficult. And if you want to try it out yourself, you can look at this picture here and try to find some duplicates. I won't leave you more than 2 seconds or so to do it, just to show you that it's a difficult problem, but I'll show the slide later on if you want to find some more, right? But clearly it's an overwhelming problem finding duplicates here, right? All of them. So we can do a little bit better, right? First of all, we don't have to compare records with themselves. It's obvious, right? Also, we only need to make half the number of comparisons because it doesn't matter in which order you compare, right? Because usually the similarity measures are symmetric. And then this is still too much. And so what people do are 2 techniques. Either they do blocking. They say, I'm only going to compare people within the same zip code. So you just have these smaller blocks where you need all these comparisons, right? That's one idea. The other idea is windowing, that you just order everything by zip code and then you run a window over your records and compare only within that window to reduce the number of comparisons that you need to make, right? And these are very, very effective techniques. They work very well. And just to give you a nice visualization that this actually works, this here is this very same matrix, just with, I think, 10,000 records. And again, we've ordered by zip code, and the blue are the highly similar records. So if indeed you slide a window over this diagonal, you will find most duplicates, right? So this is, as I said, very effective. You will have some pockets of duplicates elsewhere, but if you then do a second ordering by something else, the hope is that they will then end up in this diagonal in the middle. Okay, so this is just one idea how to reduce the number of comparisons. And the second problem is, how do I compare, right? And the traditional way to compare 2 records is just to write a rule. If the zip code is the same and the distance of the last name is just 1 letter and the phone number has the same substring of length 10, then it's a duplicate. You write those rules, and there are systems with hundreds of these rules man-made. Obviously, this is a super opportunity for learning techniques because you have great training data and you try to train systems to compare records. And there are several approaches. One is just to use similarity measures as features. It's a very traditional approach. There's also approaches that learn the similarity measure themselves. They just understand similarity between letters and numbers. Or you just go one step further and use a learned classifier, because this is really a classification problem. Given 2 records, are they a duplicate, yes or no? Right? And all these machine learning-based systems have outpaced the rule-based systems in the literature. They have not quite arrived in industry yet. Right? And then the last step that I won't talk about today is data fusion or record merging. So what do I do when I find a duplicate? That's not an easy task. The easiest would be say, I'll just delete one of them, right? But that's, you know, easier said than done. Which one do you delete? And what happens if you have, let's say, orders for both of those customers? You can't just delete one customer. You need to merge them intelligently somehow. Quite a difficult problem. Okay, so with this, I'm done. Well, I would say almost on time. So we looked at bad files and how to get a grip on them. We looked at bad data and some very initial ideas of how to get a grip on those with some data cleaning. And then while I'm looking forward to your questions, I do want to point out that, of course, this is not all my own work on my desk, but I have a great team of PhD students and researchers who have done all the hard work of implementing these things, coming up with ideas. So it's a great pleasure to work with all of these folks that you see on the screen, and of course with people in the past. And if you're bored by the questions, you can have a go at finding duplicates. Otherwise, I'm happy to take these questions.
Thank you, Felix. That was very inspiring, and I think it will resonate with a lot of us who really struggle with bad files and bad data. Thank you so much. Yes.
Thank you.
So I see the questions are coming, and participants are very welcome to keep posting. I'm just going to kick off with one question that came to my mind with regards to the fundamental principle of fitness for use. And so with that, you know, the automation of data preparation or data cleaning comes into doubt. And also you mentioned the precision and recall. So, you know, you started with the least favorite work of data engineers. And the question is that with these tools, you know, it is the case that the human data engineer will always be in the loop. But, you know, do we have a sense of how far these tools and the support of these tools can enhance the productivity?
So excellent question. So this fundamental principle of fitness for use obviously does not work very well for us computer scientists, because our goal is to eradicate every single error, right? And of course, this fitness for use principle just says, you know, clean it to a degree, or clean those parts that are actually useful to you. And all of the work I've presented is, in a sense, bared of this use case. We're just trying to do our very best job. And I completely agree, you know, if we would know the use case and say, look, this degree of accuracy is sufficient, for instance, you know, that would guide our tools better. But research right now is, you know, trying to do 100% and not succeeding. I completely agree. Yes. So that will be a way of approaching one another. I do have the suspicion, though, that fitness for use does not boil down to just simply saying, yes, okay, precision and recall of 80% is enough, and so we're done, and saying, yeah, that's exactly what our tools also achieve, and now it's fit for use. But the fitness for use for a specific use case probably is defined quite differently from the success measures of the methods I presented.
Yeah.
And so how ready are these things? So I liken it in a way. You know, my analogy is the following. I mean, I'm sure you've had you have these situations. Let's say in your house, in your daily life, there's something lying in your corridor, and day after day you step over it, right? Instead of putting it away, right? You step over it because stepping over that object is just easier than finally putting it away. And after 2 weeks, your spouse is annoyed and says, "Come on, you know, put it away finally because I'm annoyed by it." And this is the exact same effect with data preparation, I think, because every single task we're solving is an easy task. It's simple to write a quick script to clean up that particular problem. And I think data scientists don't realize that they're doing it again and again, or they don't worry too much about it. They're doing it again and again. Every day they, you know, fix the data a little bit this way, a little bit that way. And I think this data preparation, data cleaning research tries to give tools, tries to make this systematic, let's say, and give researchers or data scientists the tools to not have to do this manually again and again, with the exact same caveats as a handwritten script, which also doesn't always get everything right. So I'm not saying we're doing a better job than what a human can do. We're just making life easier. At least this is the thinking.
Yes.
And yes, it's never going to go away. There was a panel at SIGMOD 2 weeks ago precisely on this problem. It was titled, "Are AutoML tools selling us snake oil?" Right? By promising everything is automatic, including the data preparation. And clearly it is not. And they're just saying it is, right? So we're not there yet by any means.
Thank you. Thank you for that, Felix. So an anonymous attendees asked a similar question about, you know, the percentage of work that the data scientists spend on this preparation and what that is doing. So I hope that answers your question from the attendees. We do have another question from Alexander. Are you aware of any products implementing similar to the solutions you are proposing?
Yeah, so we have a survey out in SIGMOD record, a survey of data preparation tools, right? There was, I'll provide the slides anyway, at least on my homepage and maybe on Hoover or so. There's also a screenshot of that with a bunch of tools out there. Yes, there are, we surveyed, I think, 150 tools that claim to do data preparation. About 30 actually do data preparation in the sense that we have this in mind. So some say they do data preparation, but it's really just a visualization tool, let's say, right? And then I would say maybe 10 do it for real in the sense that they're quite comprehensive and really serve a broad spectrum of use cases. Yes, there are tools, but most of them are manual. So they're basically allow you to do data preparation by clicking on things, right? And some are advanced and do suggestions. And maybe the most advanced tool, if you're really interested in looking to this, is Trifacta. So Trifacta is a product out of UC Berkeley, but it's a big product, a huge customer base by now. And it's, let's say, from my point of view, the most advanced commercial tool.
Thank you, thank you. So we have another question from Oscar in the Q&A, and then we have a couple of attendees with their hand up. So Oscar is asking, thanks Felix, amazing and valuable keynote. Don't you believe the motto quality over quantity in data management environment should lead to justify the need for conceptual modeling? Indeed, bad file, bad data, bad results seem to be the result of bad models or no models at all. Shouldn't conceptual modeling play a more crucial role in this working context? And is it true to say that lack of models means potential bad data?
Yes. Absolutely. I think we had this exact same question yesterday as well, right? So this seems to be like a good question that you can always ask. And of course, the answer is always yes. But basically what has happened, at least in database world, is that we've moved databases more and more in a direction that less and less or fewer and fewer modeling is needed, right? Think of data lakes, think of document stores, think of key value stores. All of these are efforts to reduce or eliminate the need for modeling. And of course, you know, some in the audience are cringing now and say, oh God, you know, how can this happen? But it's real. And yes, indeed. I mean, we could start even earlier and say standardization, right? So there is a standard for CSV files, right? But nobody uses it, right? So there's a model for CSV files, but it's just not adhered to, right? But also conceptual modeling, of course, I completely agree. But many of the use cases that we see are integration use cases, right? So if you're within a company and you have your data warehouse and everything's modeled nicely, hardly any of the things I just mentioned apply. You know, that's a nice working environment. Yeah, you can have some data errors and you have cleaning pipelines, everything works nicely. So, but the thing I'm addressing here mostly is really like these ad hoc data science projects where you do integrate. And of course, there's, you know, you could argue it might not be worth to create a large conceptual model for this one-shot data science project. You know, it might be worth it, but apparently many users don't think that is the case. And then they do run into these kind of problems. So a resounding yes.
Good one, good one. We have a hand up. I can see here Matthias Waldeck. I hope you can unmute and ask your question.
Yes, hello, thanks. First, Felix, thanks very much for the inspiring keynote. I was wondering, many of the techniques that you introduced, they are somewhat stochastic, they work with probabilities and similarities. Now, I know from the field of data integration, sometimes we run into this issue that, well, if you consider the most similar thing, it may still be completely wrong. So what about those cases where a technique that clearly cannot be expected to work in all cases needs to kind of detect itself when it simply cannot deliver a result? So what is your take on those algorithms also being able to, well, kind of raise a white flag and simply say, well, I cannot, for instance, find the table structure?
Yeah, it's a very good question, Matthias. Thank you. So maybe as a difficult to answer. So the first comment might be, from my point of view, is that of course evaluation of these techniques should be as general as possible, so that the reported accuracy or whatever we're reporting is as general as possible, so that a user of the tool can expect the same accuracy for his or her use case, right? That's the cop-out answer here, right? So I agree, it would be even better if indeed a tool says, yeah, raise the white flag, or you know, does some cleaning or preparation, but says I couldn't capture everything. For data preparation, actually, it might be easy because the user will immediately see, does the file load now or doesn't it, right? And if it doesn't, apparently the tool didn't do its job all the way. But I agree, there are much more difficult cases where, let's say, the data loads, but there's still problems inside. Yeah, I don't have a better answer, Matthias. I could say yes, it's an open research question, right? But I think that's all I can say here.
Matthias, have a look also at the best paper from CAiSE 21. Sort of similar discussion there about internal validity. So very interesting, very valid question there. We have got one more raised hand in the time that we've got. That is Imani Gala. Would you like to ask your question?
You're on mute still, if you're already asking.
Yeah.
We can't hear you yet.
Yes. Okay. Maybe Imani is having some technical problems. Imani, you're very welcome to type your question into chat or Q&A, and we can put it to Felix at another time. I'm just going to have a quick look at, maybe we have time for one last question. Giacomo, let's look at your question. So thanks for the talk. Today we have seen data cleaning under the assumption that only one possible correction is possible for data. What about if we are not sure and multiple possible cleaning are possible? Yeah. Does data provenance preservation might help for later data management and post-processing steps?
So there are a lot of great models to do this, right? So you can make everything you do probabilistic, in the sense that you say, okay, it's, you know, we're not going to assign the one correct value. We're going to say, you know, this is Arizona with some probability, and this one is New York with some probability, and then you can carry that through to your analysis, et cetera, et cetera. To be honest, I don't see how this is done in practice. There's lots of research on precisely these kind of things. In practice, of course, it depends on your use case, right? If you're going to send out a mailing to a customer, you have to decide which state it is. You can't just put a probabilistic address on your envelope, right? If you're doing analytics, of course, or trying to train a model with your data, then, you know, they will be able to swallow, you know, incorrect data, and they will be able to take in probabilistic data. So absolutely, this is a problem. But I've worked with many collaborators in industry, and they won't have it, right? They want an actual answer. They want the correct value. This is my experience. There probably are use cases that I'm not aware of where, you know, this kind of reasoning is fine. There's also a huge research on probabilistic databases, but I'm not aware of a single commercial product of a probabilistic database out there. So I think, you know, we researchers, if we want to make impact on this area, I think there's still some way to go.
I did promise that as a last question, but we have one more, Felix, from Ruth. So thanks for the nice presentation. I have a question regarding the generalizability of the data preparation tools. It seems to me that they are very focused on open data or external data files from a company perspective. How applicable are these tools to data sets from relational databases, which are most common data sources for organizations? And how often do the problems you address with this tool set occur in data sets from ERP systems, for example? Yeah.
I don't have statistics, but indeed, I mean, if data sets are internal, they are usually easier to handle because you know the model, you know the errors you've probably already cleaned with, I mean, hopefully within your database before exporting. And so many of the problems don't arise. But just think of a company, let's say, that instrumentizes its web page or has sensors attached to its machines, etc. So you still have all these different data sources even within an organization, right? And you have different date formats, different ways to represent first names and last names, you know, comma separated this way or that way. So you still have many of these data preparation problems, but I would agree you have less of the file ingestion type of problems. I can't give you a number, but I do speak with colleagues in industry, and even within companies, they have that. For instance, we have, you know, one of my former PhD students works for Get Your Guide. It's like a travel a website, and they're doing these kind of, you know, experimental data science runs, and they, for each of these things, it's still an ad hoc study. They still need to gather data from different places, and they still need to do data preparation, maybe not quite so much in dealing with wrong apostrophes within a file. Okay.
Thank you, thank you. I can see the audience is very occupied in finding Simpson duplicates now.
Here's one solution. Here's one solution.
Okay,
there are more.
There we go. Thanks for that. Yes, I think there was a lot of chatter going on about who find whom. Okay, thank you again, Felix, for a very inspiring and very helpful talk. It's a problem that sits with all of us, and your pointers to some of the tools and advancements from research are much appreciated. So colleagues, please join me in thanking Felix for his talk, and we will resume again in, so I don't want to say the wrong time, Marcello.
About half an hour.
About half an hour.
11 a.m. Central European time.
Okay. Okay, thanks for that. Thank you, everybody.
Felix.
See you in half an hour.
Thanks for having me. And I'll be monitoring also the Whova site. So if you want to get in contact with me there, I'll be reading that.
Awesome. Thank you, Felix.